So the value nearby, the value at the nearby point to a pi over 2a, the main contribution will come from these first three terms. If we look at the higher order contributions, they're going to be getting smaller and smaller and smaller. So we're thinking of h and k being small, less than 1, so that when you square them, they get small. And indeed, these higher order terms have increasing parameters in the front of them, because you have this 1 over n factorial term. So that's shrinking down the contribution from the higher order terms as well. Okay, so we're going to need our partial derivatives. So df dx is the derivative of sine x times y with respect to x. So that's going to be y cosine of xy. The first order derivative df dy is going to be x cosine x times y. And let's just get the second order ones as well. d2f dx squared. Okay, so we're looking at differentiating this thing here with respect to x. Well, it's not too hard. You still see a constant times a cosine of a constant times x. So it's still basically just the derivative of cosine. And you get an extra factor of y out the front. And a similar thing for d2f dy squared. It'll be minus x squared sine of x times y. And of course, you have the third second order partial derivative, d2f dx dy. So there, say we look at the x derivative, and we want to differentiate this with respect to y now. But that's going to require the product rule, because we see a product of functions of y there. So it's going to be cosine of x times y minus xy sine x of y. Okay. Okay, so now we've got all the first and second order partial derivatives, so now we can look at evaluating these two terms, d of f and d squared of f, evaluating them at the base point a and pi over 2a. Okay. So d of f at a pi over 2a, this is h df dx plus k df dy, all of it evaluated at a pi over 2a. So we won't write down too much stuff, we can just do that in our heads. You see, so when we have this term x times y, when you're multiplying those two together, that gives you pi over 2. So, but in each case, you've got cosine of pi over 2. Yeah? Cosine of pi over 2 is 0. So both of these coefficients here are equal to 0 when we evaluate them at a and pi over 2a. Okay? Cosine pi over 2 and cosine pi over 2 as well. Okay? So it's just all amounts to 0. So there's no there are no terms in h and k. None of these order 1 terms in h and k are actually present in the Taylor series. Okay? In the Taylor polynomial approximation. So that's why we, so if you only included these two terms in the Taylor approximation, we'd only be approximating the value of the function as just equal to the value it had at the base point, which we're not detecting any change, we're not taking account in any change of value there if we just went to order 1 term. So that's why we go further to the order 2 terms. So d2 of f evaluated at a and pi over 2a. So this is h squared d2f dx squared plus k squared d2f dy squared plus 2hk d2f dx dy. And again, this is all evaluated at a pi over 2a. We've got these all on the screen here. So yeah, we do get stuff here. So the product term x times y gives us just pi over 2. So we have sine pi over 2, sine pi over 2. So those are just the ones. And then it's the minus the square. That's going to be minus a squared. This is going to be minus pi squared over 4a squared. Then we got this term where we got cosine of pi over 2. So that's nothing. That's 0. And then you got minus the sine pi over 2, that's again 1, and then you got this product term here, which is pi over 2. So putting all that together, so multiplying h squared we have minus pi squared over 4a squared times h squared. Multiplying k squared, you've got d2f dy squared, so that's just minus a squared. Minus a squared times k squared. And then you got the 2 times hk, and that's multiplying this one evaluated at, or the x times y is pi over 2, so you get 0 from there, and you just get minus pi over 2 from there. So you get minus pi over 2 times 2 times hk. So I think that just comes down to minus pi times hk. Okay, so you've got all 3 order 2 terms surviving. You've got a h squared, a k squared, and a h times k, which is good. But now there's quite a lot of similarity here between the coefficients. So we maybe might hope there to be a nice factorization there, and indeed there is. When you've got h squared, k squared, and h times k, so maybe you can factorize it as the square of a linear term. Well, they're all negative, so if I put a negative out the front, so is this h times k? So what do you have to have? Well, we'd have to have an ak there, get the a squared, k squared, and then to get this h squared, we'd have to have pi over 2a. I think that's right. We're just squaring all of that. Yeah, so when you square this bracket and flip all the signs to minuses, you get exactly what we had there before. Okay, so it's just, there's nothing too difficult there, but just careful substitution of the x and y coordinate into those various second order partial derivatives. Any questions so far, or any queries or things you'd like me to clarify so far? So what we're doing, we're setting out to examine the Taylor series at a point close to this base point, a over 2a. I haven't said what a is. A could be any value. So we're going up to order 2. We've got all the partial derivatives. We've evaluated these 2 bits here. So we can now return to the Taylor series. Return to our Taylor polynomial, let's call it. It's not the series. So this is the one we set out at the further up the page. So this is f at a plus h pi over 2a plus k. So we now put our nice version of this. So first of all, was f evaluated at the base point? That we said was 1. And there was no order 1 terms. The d of f evaluated at the base point. Remember, that came to 0. And then the d2 of f, well, we have a half of it, and it's got a minus sign, so it's minus a half of pi over 2a times h plus 8k squared. Okay, and then there are higher order terms. Okay, so there might be order 3 terms, order 4 terms, etc. Well, there will be. But this is what it looks like up to order 2. Now remember, if we're talking about, all we're interested in is detecting the behavior of the function close to the base point. So close to the base point at a pi over 2a. So we're thinking of the changes in h and k, the changes h and k being small quantities. So therefore, the value, if we could look at the full infinite polynomial, well, the value really is going to come down to the behavior of the h and k in here. Okay? So this is the order 2 terms. And if h and k are very small, less than 1, then the higher order terms are going to be much smaller than the order 2 terms here, as long as we go sufficiently close to the base point. Okay, but you can tell what the relationship between the nearby value and the value at the base point itself. Okay, because this is this constant value 1 minus a square. So this square term is always going to be non-negative. Okay, it's always going to be greater than or equal to 0 because it's a square. And we're always subtracting it. So we're always going to get a value less than or equal to 1. Okay? So this will be less than or equal to 1 for all sufficiently small h and k. Okay, being a bit vague about sufficient, how small exactly. Well, if you go very close to the base point pi over 2a, you will be taking the value 1 and subtracting some positive amount. So so that's i.e. less than or equal to f at a pi over 2a. So at the nearby point, we have a smaller value. Yeah. So that confirms that it is indeed a maximum.
Were we given that it was equal to 1?
No, we worked that out because remember it was just sine of x times y. So when you multiply the two values, the a's cancel out, so it's just sine of pi over 2. Yeah, that's a good question just to keep checking that. Okay, so we saw that it was 1. And that's this value here. This 1 here, the constant term in the Taylor series, that is the value of the function at the base point. So you can see it there as well. Yeah. So this shows that a 2 over a is indeed a local maximum. And this is for any a whatsoever, for any value of a. So if you look at all these points together, all the points a at pi over 2a, that's a curve in the plane. And be these kind of curves here. Oops, sorry. That's an awful drawing, but you get the idea. Let's draw it again. So you got your coordinate axes, your x and y coordinate axes. Okay, so just being very imprecise slightly. I'll show you a precise picture in a moment. So when x is 1, y is pi over 2. So if this is x equal to 1, y is pi over 2. When x is minus 1, y is minus pi over 2. Yeah. Okay. That's what the curve looks like. So what we're saying is that all the points on this curve are maximums on the surface, local maximums, and the same for this curve here. Okay. Because this is a 2-branched curve. So this is the curve y equals pi over 2x. Okay, that's the curve shown in red there. So here's a better picture of the curve. If you got MATLAB to produce you a plot of this curve, this is what it's looking like here. Okay, x and y are slightly, different way around. But you can see here the present. So this curve, a pi over 2a, or x, this curve where you've got y is equal to pi over 2x. This is one branch of it here. This kind of ridge of maximum points along here, and this is the other branch of it here. Okay. So those two parts of the surface, the two parts closest to the origin, that's these two curves here. Okay. Now you can see that that kind of structure is repeated at higher values of, or at higher multiples of pi over 2 as well. If you look at higher and higher odd multiples of pi over 2, that will get you each of these successive ridges of maximum points as you move away from the origin. And obviously, there's corresponding troughs of minimum points as well in between all of these. Can't see them so clearly because they're hidden down below. And they'd be at those would be at the even multiples of pi over 2. This similar looking curves, y equals something times 1 over x, but at the even multiples of pi over 2. Okay, so that example shows us how we can use the Taylor series to explain some of the stationary point behavior for points on this surface. Okay. Any clarification questions or any questions at all based on that? Okay. Okay, so just what I'd like to end with now is to make use of this Taylor series again. Again, we're focusing on the link between the Taylor series and the stationary points to explain the reason why the classification of stationary points is as it is. Okay, so recall that the stationary point AB, we classify that using the Hessian determinant. Classified using the Hessian determinant. D. Remember, D is the product of the second order partial derivatives minus the square of the mixed second order partial derivative. Okay, so we evaluate this Hessian determinant at the point AB. And if D is greater than 0, then if the x derivative was greater than 0, we had a local minimum. If the x derivative was less than 0, we had a local maximum. And if d was strictly less than 0, we had a saddle. So that, in a nutshell, is the classification scheme, or in a box is the classification scheme. So what I wanted to do was just to justify that. Okay? So we didn't really provide any proper explanation of why, why is it that if this Hessian determinant thing is positive, it goes like this, and if it's negative, it goes like the other. Okay. Okay, so are you having difficulty reading that? Or yeah. Which bit? Using the Hessian determinant. So this was named after someone. Hessian. Hessian determinant. Okay, well, assuming that at the stationary point, this is just to remind you, at the stationary point AB, we already have that df dx and df dy, those are both 0. Okay, at the stationary point. So then if you look at the Taylor series approximation, the first relevant term is going to be the second order term. Okay? If you evaluate the function f at points nearby this base point, because the two first order derivatives have vanished, the first contribution to the Taylor series, first non-constant contribution to the Taylor series, comes from the second order partial derivatives. Okay? So assuming that these first order partial derivatives vanish, the Taylor series gives us that delta f, so by delta f we mean the value at the nearby point minus the value at the base point itself. But this is going to be approximately the second order terms from the Taylor series. So this is going to be approximately 1/2 of h squared d2f dx squared is k squared d2f dy squared is 2hk d2f dx dy. And there's higher order terms, but we're talking about determining its behavior close to the base point. So again, those same comments say that really it's all going to come down to how the second order terms behave. Okay, so this comes from the Taylor series. Normally, when you look at delta f, you'd expect to see the order 1 terms there as well. The something times h plus the something times k. But in this case, we don't, because those first order partial derivatives are equal to 0, so they're not present. Okay. And so what we need to do is, you see, if the point AB is a maximum, then this difference we expect to be negative. Okay, so we're looking at the value at the nearby point minus the value at the stationary point. So if the point AB is going to be a maximum point, we expect this quantity to be negative. If it's going to be a minimum point, we'll expect this to be positive. The value at a nearby point minus the value at the stationary point. Stationary point is minimum, we expect this to be positive. And if it's a saddle point, then we expect the sign of this thing to vary with h and k. Sometimes be positive for some choices of h and k, and sometimes be negative. So remember, the saddle point had this mixture of behaviors. Along some certain direction, saddle point acted like a minimum, and along the other direction, it acted like a maximum. So we need to determine, we need to investigate the sign, positive or negative, the sign of this. Okay, and the way we do that is with a little bit of algebraic manipulation. We don't yet see exactly the Hessian determinant. Okay, remember, the Hessian determinant is this thing up here, the product of the two second-order partial derivatives, d2f dx squared, multiplied by d2f dy squared, minus the square of the mixed second-order partial derivative. Now we can see the individual ingredients there in here, but we don't see them multiplied together. Okay? So to bring that structure out, we rewrite this by factoring out, let's say, the x derivative there, by factoring out the second-order x derivative. We'll ignore the sign of We'll ignore this half here, because I'm only interested in analyzing whether this is positive or negative, and looking at the sign of this. So the fact that it's divided by a half is neither here nor there. Okay? I'm just looking at the sign of this. So the sign of this is going to be the same as the sign, and I'm going to divide out by d2f dx squared. And see what the effect of that is, because dividing out by d2f dx squared, that will cause extra factors of d2f dx squared to come in here and multiply the other terms. Okay? So we're going to have a h squared here, and this is going to be multiplied by the square of d2f dx squared. Okay? So I'm dividing out by it. So to compensate, I better multiply by it. And then it's going to be, I'm going to have k squared times d2f dy squared multiplied by d2f dx squared. Because again, I'm dividing out by it, so I need to multiply it by it to compensate. And then we've got our 2hk, got my d2f dx dy, and again, this is multiplied by d2f dx squared. This. So what I've done there looks kind of artificial. Okay, I've pulled out this factor of 1 over d2f dx squared, and of course that introduces extra versions of that factor in each of those terms to compensate. So I haven't changed the thing, I've just multiplied and divided by the same amount. I've dropped the half, remember, because I'm only interested in picking up the sign of this thing, so I don't care whether it's a half of it or not. And now I'm looking to complete the square, okay? Because the reason I've done this is now this structure inside the bracket is slightly easier to recast as the square of something. Okay. So I've still got my 1 over d2f dx squared here. Well, the thing I'm going to choose is the square. That's kind of dictated by the behavior here in the h squared and the k squared. Obviously, I can take the square of h times d2f dx squared. Sorry. H times d2f x squared, and then multiplying the k over here, I will have k times d2f dx dy. So I'm going to take the square of all that. Now that isn't the complete story. Let's see what we get from squaring this. When I square this bracket, I get this term here, h squared times the square of the x derivative. I get all this here, so I get 2hk times the product of these two. So I pick up all of this. And then I also get plus k squared times the square of this mixed second order derivative. So I'm going to have to subtract that off because I don't see up here anywhere a square of this mixed second order derivative. And then I have to add on this term here, because this middle term here isn't generated by that square. So I still have plus k squared d2f dy squared d2f dx squared, and then I have to minus k squared times the square of d2f dx dy all squared. And then I still have this big bracket here. Okay, so it's kind of artificial at first glance. So I pulled out this factor, 1 over the second order derivative. That gave me all these. Then I recast that as the square of this linear term in h and k, and that gave me most of it. Well, gave me some of it. So I still have this term here, and I want to subtract off k squared times the square of this. because that comes from squaring this factor here, but I don't see that up there, so I need to subtract it off again. Okay, so the reason this is good, because I have 1 over d2f dx squared here. This is the square of something involving a h and a k. I'm now no longer that interested in exactly what's going on in there, because it's a square of something. Remember, I'm trying to decide the sign of this thing. And if it's a square of something, I know that that part is always positive. And then here I have plus k squared, because I can pull out a k squared there. And here we see the Hessian determinant again. So this is how the Hessian determinant comes into it. d2f dx dy, all of it squared. So I need a large bracket there. So that there is the presence of our Hessian determinant. So remember, I'm trying to classify this stationary point AB as a local minimum, local maximum, or a saddle point. What this quantity we're looking at here, what is it? It's the change in value of the f when you evaluate it at a nearby point minus the value at the stationary point itself. So I'm interested in the sign of delta f. If it's always positive, I know I'll have a local minimum. If it's always negative, I'll have a local maximum. And if it's a mixture, if sometimes positive, sometimes negative, I'll know I'll have the saddle point. So the question is then, looking at this quantity, what sign does this quantity have? Is it positive? Can I say it's always positive? Can I say it's always negative? Or are there some situations in when it's a mixture? Well, if we just look what's inside the big bracket here, I've got the square of something, that's always positive. I've got plus the square of something, that's positive still. If this bracket here, which remember is the Hessian determinant, if that's positive, then everything I'm seeing in this large bracket is positive. So that's good. So if the Hessian determinant is positive, then the sign that this whole expression has just comes down to the sign of this thing here. Yeah? So if the Hessian determinant is positive, this whole big bracket is all positive. So the sign of the whole expression is just determined by the sign of that thing there. Okay? So if the Hessian determinant is positive, the sign of this is the same as the sign of this factor over here, d2f dx squared. So if the d2f dx squared is positive, this whole thing is positive. So it's a local minimum, because the function has a greater value at the nearby point. If d2f is negative, this whole thing is negative. So delta f is negative, so therefore the value at the stationary point must be higher than all the minimum points around, all the nearby points around, so it's a local maximum. So if d2f dx squared is greater than 0, it's a local minimum. If it's less than 0, it's a local maximum. But that's all if the Hessian determinant is positive. If the Hessian determinant is negative, then what we see is a whole mixture of positive stuff, negative stuff, added together, multiplied together. So it's up in the air. Maybe it's positive, maybe it's negative. What particular sign it has will come down to the choice of h and k. What signs h and k have and how big they are in relation to one another. Okay? So if the Hessian determinant is negative, I've got a positive thing here competing with a negative thing here. So it'll come down to the choice of h and k, how big k squared is compared with the size of the term inside here. Remember, this h and k are multiplied by those things there. Okay. So if, on the other hand, the Hessian determinant is less than 0, then the sign is unclear. In other words, it depends on h and k. For some values of h and k, it will be positive. For other values, negative. And the sign is unclear, i.e., it depends on h and k. So it must be a saddle. Okay. Delta f, difference in value between the function at the nearby point and the base point. It's not always having the same sign. That means for some nearby points you get lower value, for some nearby points you get higher value. Okay, so that goes a lot of the way towards proving that classification scheme. Okay, it's the main idea between why the Hessian determinant has the significance that it has, why its sign controls the sign of the nature of the stationary point, and why, when the Hessian determinant is positive, why we have to come and check the sign of this thing here. That's because the sign of the whole thing is going to be determined by the sign of this quantity over here. Yeah. And it's also good, so we see the Taylor series approximation playing a central role. Okay? It really is a very fundamental concept of approximating arbitrary functions with polynomial series. Okay? And it lies at the heart of a lot of mathematical techniques. Okay? Okay, so hopefully you found that useful and good background work for your work on the coursework.